I will talk about large-scale ship installations without risk and investments. It will be some of it will be very much along the lines of what Jürgen said, but I will put it into the context of how we do it in Heliac. Very briefly, Heliac is a relatively young company. We were established back in 2014, and we are based in Denmark, just north of Copenhagen in Denmark. And we are producing, as I will show you, a new solution for high temperature solar heat. I will take you through an agenda presenting you about our technology, the opportunity we see out there, the challenge, which is very much about the challenge when we put it into a Malaysian context, which has to do with energy prices and with solar conditions. Then how to get to lower costs, and then finally what we call heat purchase agreements, but which is similar to Jürgen's presentation. First, what we do is we produce these panels. It's basically very large magnifying glasses that we are producing. And this is from our first and so far only installation. It's a 1.5 megawatt solar field, which produces heat for a district heating plant in Denmark. So I will very briefly take you through how it works, because that makes life a little bit easier to explain. So if I stop the video here, what you can see here, these magnifying glasses, each of them are 2.5 square meters. So a panel is around 20 square meters. We have 88 of these. It's a Fresnel lens for those of you who are engineers. They are transparent, and the light goes through them. And where the focal point, a few meters on the back, we have a small receiver. Through that receiver, we run a liquid, and the liquid heats up because it gets very hot in the focal point. It integrates into, I'll just hop around here just a little bit. It integrates into this district heating plant, which could just as well have been an industrial production facility. How this specific plant works is that we have a water tank here. It has around 400 cubic meters. The hot water is always on the top of the tank, and we have the cold water down in the bottom. When we use district heating, which you probably don't have much of in Malaysia with 30+ degrees every day, they will take out the hot water from the top of the tank, run it through the village over here. It comes back cold, 40 degrees, and is returned into the bottom of the tank. When this tank needs to be heated again, you will take out the cold water from the bottom of the tank, run it over a biomass or a gas burner over here, and return it to the top of the tank. So this is how district heating works, and this is how you would do it with many industrial processes also. Just have to replace the houses with that industrial process. What we have done is that we have also integrated into this. So when we have sunshine, we take out 40 degrees from the bottom of this tank. We run it through 6 panels, heat it up to 95 degrees, so about 1 centigrade per lens, and return it to the top of the tank. So 2 things. This is first of all, it's a very, very simple process. That's that works from very well-known physical processes. And the second thing, it is very, very simple to integrate into existing solutions. So we will always be a supplement to what the customer is already using, and they will not be in risk of running out of energy on cloudy days. So that's the very simple part of it. If we just take a schematic look at it, it's again, just to show you, you have the light coming through the lenses and it hit the small receiver. You have a cold liquid coming in, it heats up for every receiver, and it goes out hotter and it goes to the next system. So very, very simple. The entire structure is based on standard steel and aluminum components. The lenses are made out of standard windows glass, and the structures that we produce are put on the back side of the lenses, so it's protected against most wear from the weather. So super simple, and this also makes it simple because the lenses are flat. This is also very important. We can design it so that when we have when we have windy conditions, we can go into a horizontal mode, and then we will have no cross section to the wind almost. And this makes the entire structure very simple. I just realized this is not because you are not allowed to see me, but I realized that I actually had a blocker on my video camera. So now you can see me as well, some of you at least. So very simple structure, and that of course is a part of how to lower the cost. Just to show you the efficiency, we're here just playing around with a piece of wood on a sunny day. And as you can see, we can put this on fire within basically a second. We can go to very high temperatures. We actually don't know exactly how high, because our thermometer melted when we came to 1200 degrees. But we know that we can melt aluminum and steel and things like that. So very high temperatures. So the heat generation is really not the limiting factor. It's more how to harvest the heat and transfer it to systems in a useful way. This simplicity also makes it a very versatile solution. We can produce the heat for any kind of industrial processes and district heating. What we are really doing is we are delivering the solar field. We have a closed loop where we produce the heat, we deliver it at a central heat exchanger, and then the customer will have his own closed loop here and take out the produced heat. So if this customer is using it for food and beverage production, or if it's for heating other things, or if it's for cooling, or even for power production, if you go to higher temperatures, it doesn't really matter for us. All we need to know is where is the solar field, or where is the customer situated, and how much energy do they need, and at what temperatures, and then we design the solar field for delivering that amount of energy at those temperatures at this contact point. Of course, you can also include a storage, especially if it's below 100 degrees, then storage is very inexpensive, but you can also use other storages if necessary. So it said on the first slide, we are specifically looking at temperatures below 200 degrees, even though we can go higher, and I'll just try to explain you why. First, the solar thermal benefits. Of course, you know that it's without emissions, and some of you are probably also very concerned about the rise of carbon taxes in the future. But we also think that what we see is that many of the potential customers we talk to find solar thermal very interesting from the point of view that you will not have price fluctuations. And many of them are not really aware that we can harvest 3 times as much energy per area compared to solar PV. So our solution does not go on rooftops. We are going for much higher, much larger installations, more than what's room for on a rooftop. But if you want to produce X amount of kilowatt hours of heat, then you will get 3 times as much energy per area than if you had put in solar PV and converted that into heat. The specifics of the opportunity we see below the 200 degrees is we try to show this. This is from a report from the National Renewable Energy Lab in Colorado in the US, looking at how is heat demand distributed across temperatures and amounts. So if we look down here, we can see that temperatures up to 200 degrees, that's around 7,000 tera BTUs. And if we want to go to 400 degrees, what other solar thermal solutions sometimes try to do, we only gain a little bit more in the potential market size. So it's the really big market is down here, and then you need to get to the very high temperatures to produce steel or glass or cement. and this is out of our reach. So, but staying below 200 degrees, we are looking at around 10% of the total final energy demand in the world. So we think that's an attractive opportunity to go for, and especially because it's very hard for most solar thermal solutions to produce heat above 100 degrees in a competitive way, which I will show you in a few slides. First, this is another way to present some of what Jürgen said before. Process heat below 200 degrees is basically what you use for any kind of industrial processes other than steel, glass, and cement, and a few others. But almost all products are produced like this. You need to heat something, you need to boil something, you need to sterilize it, you need to pasteurize it, you need to dry it. It's all the same temperatures. Most of it is around 140, 160 degrees. When you look at it from the perspective, from an economical perspective, it's also very interesting to go to the higher temperatures, because many companies have processes at 60, 70, 80 degrees, but they also have processes at 160 degrees maybe. And if you cannot, and today what they do is they produce the 160 degrees by burning gas, and then afterwards they can then distribute the heat at the right temperatures throughout the system. So if you come with a lower temperature, you need to have two systems sometimes to integrate the heat. If we come with our temperatures at the same temperature as the customer is already using as a max temperature, it's lower cost for integrating it. If we look just at a few examples, these are just desktop examples. It's a few industries that I found on Google Maps in Malaysia. It's just to show you, do we have room for installations on the ground? And if we look at one of the most interesting industries seen from a process heat perspective, then it's pulp and paper. It consumes around 1% of all energy in the world, as far as I can see at least. So we have a pulp and paper factory here in Malaysia. And if we were to provide them 30 gigawatt hours at this specific location, we would need an area of this size. This is a pretty big solar field actually, but the point is that there is lots of land around. This is how it looks in most parts of the world. The infrastructure that you will have a large city somewhere in here, and then you have an industrial zone, and then you have farmland around, which actually allows for these solar fields to be built. It seems like that. I tried to look around in Malaysia, and it looks like it's slightly more challenging in some places in Malaysia, where you sometimes have the large industries inside the cities, which of course makes it more difficult to find room nearby for the heat production. But it's a very, very large market if we look at it at the potential globally. Similarly, if you look at the food and beverage market, it's basically all kinds of foods are produced at the 60 to 200 degrees. This is a Nestle factory I found somewhere also in Malaysia. And again, I tried to show you that a 30 gigawatt hour per year solar field there's room for it, at least. And very important, just to stress it again, I have not talked to any of these two companies. This is just, it's just what we do every time we make a presentation. We try to find a food company and a pulp and paper factory somewhere in the local area, because it's good illustration. So, but Malaysia is a bit challenging because it's all about money, really. And what we try, at least in Heliac, is we are trying to offer heat at the same cost as natural gas for the local consumer. So they will have no extra cost at all. What's challenging is that you have quite heavy subsidies in Malaysia for fossil fuels. So the cost of gas for an industrial user in Malaysia is almost half of the global average. And it's less than a third, almost a quarter of what we have in Denmark. And considering that the The economics of a solar field or the competitiveness of a solar field is a combination of what are the local cost of gas and the local solar irradiation. And since Denmark and Malaysia have more or less the same solar irradiation, it's difficult to see a solution being built in Malaysia as costs are right now, unless of course there can be significant subsidies for the solar thermal as well. But when you're a company like ours, you would prefer to find the most sunny countries in this part of the figure and say this is really where we can make be most competitive against the natural gas. Another way to look at it is to say, well, if we were trying to compete with natural gas in Malaysia, then again, it depends on how much the sun shines. This is the bar showing that. DNI is more or less the numbers of hours of full sunshine during the year. So the less the sun shines, the lower we have to price our solar field in order to be competitive with natural gas. And the challenge here is that, which I will show you on the next slide, is that no solar thermal solutions, as far as I'm aware, is able to even provide competitive pricing without subsidies in the most sunny areas of Malaysia as it is right now. This is which is what I'm trying to show you here. This is a figure that I have found from the Australian Renewable Energy Association, where they have looked into what is the cost of producing heat with different solar thermal solutions. So first of all, if we just look at the dotted line that I put in down here, the blue dotted line, this is really the cost, which compares to what we had on the previous slide, that solar thermal needs to hit in order to compete with natural gas. Then we have the different kinds of flat plate collectors that you also have in Malaysia. The challenge here is that as soon as you start to get above 100 degrees, the cost of producing the heat increases significantly because the efficiency of the panels go down. Then to get to the higher temperatures, you need to go for the different kind of mirror-based solutions, the towers and the Fresnel lenses and the parabolic trough. And all of them are significantly more expensive than what is allowed for under a Malaysian solar conditions and Malaysian gas prices as they are right now. And then I've tried to put in where we are, and at least we are a bit closer to the dotted line. And I hope that we will eventually actually get down where it could be interesting for Malaysia as well. Just a final thing, at least here in Denmark, there's a lot of people that seems to think that we can just produce heat by using electricity. The challenge is that in general, electricity costs 4 times as much as heat. So even though you can convert electricity to heat with almost no loss, you will actually have to pay still 4 times the cost than if you had burned natural gas. So if you are in the lower process temperatures, you're below 100 degrees and you only need to raise temperatures maybe 20 or 30 degrees, you have very good options in heat pumps and similar technologies, but going higher, heat pumps can't really contribute with anything. So can we get the cost down? Well, if we look at, we're really looking at economies of scale, and if we look at how the economies of scale has been in other industries or are expected to be, we can see some very significant drops in cost, and we can't see why this shouldn't happen in our industry as well. Solar PV is an extreme because of the way that solar PV is produced. So you have this very high or steep drop, which will not be seen in other industries. But if you look at wind, it's very likely that you can cut at least half or even more of the cost of your technologies by getting into scale. if we look at our specific solution, we can see that we should be able to get cost significantly below, lower than 50% lower than where we are now, simply by getting a bit to scale, because we know what the components that we use, what they cost if you buy enough of them. And so far, we definitely do not buy enough of them. So we are paying a much higher price than we will once we get to scale. So we believe we are at least at the 50, maybe at the 70% cost cut sometimes in the future when we get to these larger areas. Another very important component, which is also sort of into what Jürgen was talking about, is the cost of capital. So it's very much about the cost, the risk cost. The way this small graph should be read is that, again, just like in the map I had of Malaysia, what is the maximum price you can take for a solar field per megawatt hour, per megawatt thermal under these conditions. So if you have to pay 8% in interest in Malaysia, you would be able to sell it at 250,000, and if your interest is down at 0, you would be able to sell the same solar field at 550,000. So it's super important to get down the risk curve here, so to get these the cost of capital down, because that allows to increase the cost of the solar fields. And as I showed you just before, the solar field costs are much higher than this, so we really need to get to the lowest point here. Again, in Malaysia, your cost of gas is around 22.5 euros per megawatt hour. In Denmark, we are talking about 40 to 45 euros per megawatt hour. So it's just very, very different conditions. If we look at what would our cost be going forward, we try to look into what has been the risk premiums during the 2010s for offshore wind turbines. And so this shows the average risk premium over the LIBOR for these solar fields, offshore wind turbines. With the existing interest rates on the LIBOR, this means that in principle, we should be able to, as the capital markets are right now, to almost get into negative territory for these green bonds once we have de-risked it significantly. There is, of course, a big difference between selling heat and selling electricity, which is the ability to distribute it over long distances, and then also to who can actually underwrite the risk. So in these cases, you will have a PPA, a power purchase agreement, which is almost always backed by a national government that promises the project developers that if you all the electricity that a specific wind park produces, we will buy at a specific price for the next 25 years. So you have an off-taker which is very unlikely to go bankrupt, so you know that you will actually have your income. On the other hand, you do have some very significant technical risks. It's not easy to build an offshore wind turbine park. And when a large-scale wind turbine goes malfunctions, you will lose maybe 10 or 20,000 euros per day in revenue, and you can't fix it from one day to the other. If you, on the other hand, have a solar thermal field financed under the same conditions, then if one of our panels doesn't work, then you will lose maybe 20 or 30 euros per day in lost revenue, and you can drive out and fix it any day you want. So very, very big difference. Then you cannot transport heat as far as you can transport electricity, but you can actually transport it pretty far. District heating networks transport heat 50, 60, 70 kilometers in many places without any significant losses. So it's more a question, do you have an off-taker or a group of off-takers at the other end of the pipe that will be able to take off to buy the heat when it's produced? So this leads me to my final point, which is these heat purchase agreements that we are looking for. So it's basically we're trying to copy the power purchase agreements from the wind and the solar PV industry. So why are we doing this? We're doing this because we want to get to scale. And we can't get to scale when sales are slow, and sales are slow because end users don't know about our technology for very good reasons, since we only built one solar field so far. They also, the very large companies that we're talking to, some global or at least very international companies with production facilities in many places, they cannot take on their balance sheet the capex of building large-scale solar fields, so they will go for the smaller scale sales initially, and things will just go slow. And then, because nobody knows about the technology, permitting processes can be slow, and when you need to depreciate your investment over a short period of time, or have a return on the investment over a short period of time, then your end user will calculate in some will end up calculating some very high costs for the energy. So with a heat purchase agreement, the end user has no capex, they have no opex, and they have no risk. And the point about no risk is, as I showed you in the very first video, is that they will always be able to produce heat the way they've always done, in case our system for one reason or the other doesn't work. So our business model is really, and now we come back again to what Jürgen talked about, the refinancing. We built a solar field with where we finance it with relatively high interest rates. We will then start selling the heat, and that will de-risk the solar field. And once the solar field is de-risked, then we can sell the future revenue at a low interest rate by refinancing the loan or having a kind of a green bond. And looking at the other side, there's lots of money out there for infrastructure projects. We can see that from the wind turbine industry and many other industries. So being able to offer very safe returns going forward is something which is interesting for infrastructure funds and pension funds and the like. For us, we are looking in general for pilot customers. We are looking for partners who can help us implement this. We are in Heliac, we are 20 people right now. We expect to grow significantly, but still we cannot be in many countries around the world at the same time and doing all the construction. We will be looking for financing partners who sees these long-term revenues as interesting. And we are looking for, until we sort of get to the price parity of fossil fuels, we are looking for subsidies that can drive the economies of scale and reduce cost of capital. So this is where we are now. I hope you find it interesting, even if we may be a bit too expensive for Malaysia for the next few years. We should be able to show up someday at least. Yeah, so this is how the panels work. Of course, this is a speed up of the process, but they track the sun through the day with a simple tracking device, and it just works and works and works. So we are happy about it. And with this, I would like to say thank you. Thank you for listening, and looking forward to the discussions and the questions. Thank you.